All right, so for this question 5 from 2018 in the scoring guidelines, here is how the points are awarded. This is a short FRQ. On the exam, when you take the actual one, not in class, but on May 12th, I think it is for you guys. Yeah, May 12th. There's going to be 3 short FRQs and 2 long ones. Okay, there's always 50 multiple choice and then 3 short FRQs and 2 long ones. And then they're weighted 50-50 in terms of your overall grade. So you'll get 90 minutes to do the 50 multiple choice, and then you'll get a break, and then you'll get 90 minutes to do the 5 FRQs, and then you're done. And you can't go back and forth. So you get only the 90 minutes to do those 50 multiple choice, and you get only the 90 minutes to do the 5 FRQs. When we take our semester exam the week after spring break, it'll be similar. We'll take 1 day. We only have 80 minutes instead of 90. So instead of 50 multiple choice, you'll have 45. Okay, so you'll have 45 to do in 80 minutes on that Tuesday after spring break, and then you'll have a break until Thursday. And then on Thursday during class, we'll do 4 FRQs because again, we only have 80 minutes instead of the full 90. Okay, so it'll be very similar to the experience you'll have, just separated by a day instead of separated by like a 20-minute break. And a slightly shorter, just because we only have 80 minutes each class period instead of 90. It'll be much like that. So that's why you see some of these that have fewer point totals and shorter time ranges, because they come in 2 flavors, short and long. All right. So for this one, in the first part, before we even look at the first part and see the answer, tell me what your thoughts are about the energy of this system. And let me unblock the screen here so you can see the pictures as we discuss it. Tell me what your thoughts are about the energy of this system, given that the block drops on at the equilibrium point. What do you think, Blake?
I think it increases because of equilibrium is kinetic energy.
It increases what?
The total energy.
The total energy?
Yeah.
Okay. Other thoughts? All right, so based on your just practical real life experiences, if this is moving back and forth and it's moving at a certain speed and you add mass to it, do you think that'll speed it up or slow it down? Okay. All right, so that's what your intuition tells us. And so the goal here is to try to see if the physics proves that. All right, and if it slows down, the mass went up, but then if it slows down, yeah, okay, so let's talk through the math of this. Now, I want to reflect back on the multiple choice question we had, just especially to review for the seniors who weren't here. It was the exact same scenario, except instead of double the mass, I don't think it even said how much more it was. It just said there was another block. And instead of dropping it on at the equilibrium point, it dropped it on when the spring was at the full amplitude. So you could say it was either fully compressed or fully stretched. When it drops on at the amplitude, what kind of energy does the system have when the block is all the way at the amplitude?
Elastic potential.
Only elastic potential. And does the mass change the elastic potential? No. And so in that case, we dropped it on there, the elastic potential stayed the same, so the kinetic energy stayed the same when it got to the midpoint, because we dropped it on at that spot where it was all elastic potential, and mass doesn't affect that. So because it had the same kinetic energy in the middle as it did before, the extra mass just meant it was moving slower. In this case, it's dropped on in the middle. So what kind of energy does it have here in the middle?
Kinetic.
All kinetic. And when we drop on mass, we've increased the mass. And so if we think about that practically speaking, that should make it slow down. So if the mass goes up but the velocity goes down, is it possible the kinetic energy stays the same or decreases or increases? It could be any of those, right? Until we prove it mathematically. Because it's got m and v in the equation, 1/2 mv squared for kinetic energy. So what we have to do is prove the scenario. So with the period, let's start with part 1. Part 1's only worth 1 point. And to get that point, you have to come up with this answer. All right, √3. So let's talk through how you get that in case you weren't able to come up with that value. What's the period of a spring? What's the equation for the period of a spring?
2 pi m over square root m over k.
All right. So we've got a period of the object when it's just block P, and it's going to be 2 pi over K. But then we also now have a second situation, right? We've got the PQ combination, both blocks stuck together, okay? And so that's going to be 2 pi. But what happens to the mass? It's 3m, right? It's 3 times the other over K. And they want you to find the ratio of TPQ, the period when they're stuck together, to TP. So if I just put that equation over this equation and see what's left, so this one is 2 pi, and this is 2 pi root m over K. The 2 pi cancels, the root K cancels, right? Most of it cancels. The m's cancel. And we just end up with root 3. So that's what they're wanting you to kind of process in part A.
I just crossed out the roots too.
All right, questions about that? So that one is just 1 point. And it just says for the correct answer, so you wouldn't necessarily even have to show your work to get that point since they only made it worth 1 point. So if you're able to visualize that in your head and come up with the answer in your head, this is one of those times where that would be sufficient, because of course you don't know that when you're taking the test, right? You don't know that this is just worth 1 point. It could be worth 2 points, and one might be for showing your work and one might be for coming up with the answer. So I would always show your work, but in this case, the way the rubric is worded, you didn't actually have to. Unfortunately, you just never know that while you're taking the test. All right, any other questions on that? We okay with the first part? All right, now we go to the second part, and it says for B, how does the amplitude of the oscillation when it's combined, so the amplitude is the distance it moves, of the 2 block system compared to the amplitude when it was just the first block, all right? And so here is, you have to give your answer in a clear, coherent paragraph length response. Sometimes the paragraph length response is in a short FRQ, sometimes it's in a long FRQ. You always have at least one. A couple of years ago, they actually had 2 in the 5 FRQs, but there's always at least one. So you have to be prepared for that. And if let me scroll down to the bottom first. So the 5th or the 6th point, this is actually worth 6, is for having a logical, relevant, internally consistent argument that addresses the required argument or question asked and follows the guidelines described in the published requirements for the paragraph length response. So paragraph length response requirements, I've got the document on the bulletin board page of Axis. You can read through that, but basically it tells you it needs to be a legitimate paragraph. You can't just have a bunch of bullet points or random thoughts. You need to capitalize the first letters of your sentences. You need to punctuate your sentences. They're not going to take away this point if you miss a comma, but it does need to look like a paragraph. Now you can break up the paragraph with equations, just like you could if you were typing out a report, but it needs to look like a paragraph, not just a bunch of thoughts or just a sequence of equations. There has to be some text clarification. And so that's a pretty easy point. It's not given though. I mean, just because you write a paragraph, if your thought process does not seem to be logical or is not consistent, like you start one way and then you change and it like the thing you argue earlier is broken by something you say later, then you could still learn this or lose this point. But most of the time, we're pretty lenient on that point unless there's just some major inconsistencies. Okay, as long as it's in paragraph form. But you could have a great explanation all with paragraph or all with equations in just a few phrases, and it's not in paragraph form, and you would easily lose it for that. Okay, so you have to put in paragraph form. Now here's how the other points are awarded. So, and it shows here, note the response is graded even if an incorrect selection is made. So in some ways, what you check here is a bit irrelevant because all the points are awarded in how you phrase the paragraph. Okay. So here is the first point, applying conservation of momentum to the collision. So let's break that down and look at the momentum. And I just gave ourselves a a screen here. So we know that the momentum, there we go. We know that the momentum of block P plus the momentum of block Q is going to have to equal the momentum of the combination after they collide, right? Doesn't matter what kind of collision it is for momentum conservation, or is momentum always conserved?
Always.
Always conserved. So it doesn't even matter what kind of collision, momentum's always conserved. It's just kinetic energy that's not always conserved. So if we think about the momentum of each of these scenarios, in the beginning, block P is just going to be the mass of that block times its velocity. And how about the momentum of Q? It's just 0 because it didn't have any movement. It's just being placed right on top. So that's 0. And then the momentum after is going to be the mass of P plus the mass of Q. Right? They're stuck together now, times its new velocity. And so we'll just call that just V. Now, so we know MP VP equals, and then what do we know about the mass of Q?
It's 2 times the mass of Q.
Yeah, it's 2 times. So now we can say, well, that's going to be MP plus 2MP times V. Tracking okay with that? All right, so MP VP equals 3 MP times V. Maybe I should make that P a little smaller, kind of looks like a variable, not a subscript. All right, so we need to figure out, the question that they want us to show here is that they're just illustrating the conservation. So you could stop here, or you could show the relationship between the two. So you could, this I think shows the momentum well enough, you could earn that point. But if we put the velocities, and let's go ahead and make this final velocity just to make it clearer. So if we put the final velocity compared to the initial velocity, that equals MP divided by 3MP. So the way they relate is that the final velocity is going to be, I'm running out of room here, the final velocity is going to be 1/3 the initial velocity. If we just rearrange, the m's cancel, right? So we get final velocity is 1/3 of the initial. Now, let me just double check the wording to make sure they don't actually say you have to come up with a quantitative, do they? I mean, it has to be quantitative enough that you know it's going to be less, but it doesn't have to be necessarily.
It doesn't really give you enough to do anything more.
Oh, well, we can do more. I'll show you some more things we can do, but yeah, I think whether you went all the way down to this step or not, as long as you showed that it says for applying conservation of momentum to get that first point. But to get the second point, you need to get all the way down to showing that the velocity is going to be less after the collision. So if we go back to the rubric here, you can see for correctly finding that the post-collision speed has decreased, in other words, that the final is 1/3 of the initial velocity. So that's your 2 points. Now, if you talk about it, it's an interesting note here. It says the first 2 points, these two, can be earned for stating that the collision is inelastic. So it surprises me that they just give you both of those points just for making that statement. But you can argue if it's inelastic that kinetic energy can't be conserved, that kinetic energy will be lost, right? If kinetic energy is lost, then it won't go as far. So it's just a different kind of an argument. The way they're showing it in the standard rubric is a much more quantitative mathematical approach. If you just said, hey, this collision's inelastic because they stick together, so kinetic energy is lost, you're taking more of a conceptual approach. Okay, so either way apparently works based on their note here. All right, the next one says for stating or implying that the system's kinetic energy has decreased or for calculating a lower kinetic energy. So if you started by saying, hey, this collision is inelastic, therefore kinetic energy is lost, you've just got 3 points and you didn't actually have to do any math, okay? But you can prove it with the math that we showed on the previous screen. We okay with the first 3 points then? A couple different ways to earn them. Any questions so far? Yeah, Andrew.
How can you say that it's the kinetic energy is decreased if the mass? Oh wait. Yeah, if the mass was like moved up 3 times, but then it's 1/3 to the relationship of the velocity.
We'll look at the math of the energy here in a minute.
Okay.
Yeah. All right. Any other questions? We'll get to his question here in just a second as we prove the math on the second part. All right, and then the fourth point, for stating or implying kinetic energy of blocks right after the collision equals the maximum potential energy of the spring. So in other words, if you can figure out what that kinetic energy is right there after that collision, then that's going to be however much elastic potential energy is in it when it stretches out to the amplitude. Or they say you could also phrase it this way, for stating or implying that the maximum potential energy when it's fully stretched out at the amplitude equals the total mechanical energy right after the collision. So there's a couple ways you could say it. They're also saying if you just state that the total energy is going to be equal to 1/2 kx squared or ka squared, since they were using a in the question, you can get that point for saying that relationship as well. Questions about the fourth point? Somehow you need to make it clear you understand that whatever kinetic energy it has after that collision, that's all the energy it can have when it stretches the spring. And then the last point, other than the one just for your paragraph structure, is for stating or implying that the maximum potential energy is reached when the displacement from equilibrium equals the amplitude of oscillation. So you have to prove that because this is going to be different, the position where it reaches its amplitude will be different, but it will be relative to this energy level. It also says the previous 2 points, so these two about energy, can be earned in a single sentence in which both or one of those points is implicit. So you can give the math kind of focus of it, or you can explain it more in words, as long as it's clear that that energy conservation is helping you determine how much it would move in terms of its amplitude. And then it also talks about down here, the first 2 points back up at the very top, you could also, instead of saying it's an inelastic collision, this seems a little bit outside of the box. I'm guessing this is one of those where some student came up with this and then they went back to the committee and said, hey, we should add this to the rubric because it actually works. If you said a frictional force is exerted on block P by Q so it slows down, it's a kind of a strange way to think about it, but it's not incorrect to say that. So, and then you would just have to say because of that, energy is lost to get the third point. So a couple notes and alternate ways you could score it. But let's go ahead and look at the energy part of this relationship. So we figured out the momentum. We know now that the velocity in the second scenario is going to be 1/3 the velocity in the first scenario. So let's look at the energy relationship now. So if we think about the kinetic energy of the system, once they're stuck together, we know the equation in general is 1/2 mv squared, but this is going to have both the mass of P and the mass of Q now. So it's going to be 3m, right? We okay with that? All right. And we know that the velocity is going to be slower, as we proved with momentum. It's going to be 1/3 the velocity that it was originally. So we can say it's going to be 1/3 v, but that is squared. All right, and let's go ahead and say vp, because it's the velocity that the initial block P had. So if we break that down mathematically, we get 3/2 here, and we get 1/9 there, right, when we square the 1/3. So 3/2 times 1/9
it's 1/6 in total.
Yeah, 1/6 in total, so 1/6, because we got 3/2 times 1/9, MVP squared. All right, now let's compare that to what the kinetic energy was initially for the block before the collision. So if we think about just block P before they stuck together, MVP squared. And so when we compare those, KPQ is going to be 1/3 KP. If we multiply KP by 1/3, we get KPQ. Is that making sense? So you don't actually have to prove it mathematically. You can prove it conceptually, like the rubric said. But this is the way that, hopefully that kind of answers your question about how it actually works out to be 1/3 the kinetic energy.
I forgot about the squared part of
Okay.
velocity, which
Okay.
makes it smaller.
Yeah.
Because then if it wasn't there, it would just be equal.
Mm-hmm. Right. All right, the last point is that if this kinetic energy is less, and that, so that 1/3 KP has to become the elastic potential energy, right? That's the kinetic energy that can turn into elastic potential energy as it stretches the spring. And since the elastic is this, that doesn't change, that doesn't change. So if the energy becomes less, this is the only thing that can become less, right? The spring constant won't change, and the 1/2 is a constant as well. So if the energy becomes less, then this has to become less. Okay, and so then we know that the amplitude won't be as much once they collide. So this is one where your intuition, if you stop and just think about, well, what do I think would happen, and don't get too caught up in the math. If you just think, well, if I drop this block on, it should slow down. If it slows down, it shouldn't go as far. Right? Just logically, that should be your conclusion. And then you can go back then after and use the math to kind of prove it. Okay? Pretty tricky one.
Didn't make sense that it would be increase in distance. Sorry.
Mhm. Yeah, but sometimes it's so quick to just go straight to the math, you can kind of trip yourself up because you've got some things that are squared, some things that aren't squared. But if you just stop for just a second and say, okay, what should that really do? I drop it on there, more math, it's gonna slow it down. If it slows it down, it's not gonna go as far. And so you already kind of have a framework of conception to then make sure your math follows that.
However, if it was dropped on, like you were saying, on the end of like the amplitude, then it would be constant still.
The kinetic energy is, but remember, because the mass went up, the velocity still goes down.
But the energy, total energy is the same.
Yeah, the total energy
And
stays
the
the same.
spring goes to the same distance.
Yes, yeah, because of where we dropped it. And so that's how, like I said, College Board's gonna give you all kinds of questions where they just mix it up, you know? One time, let's drop it on the end, one time, let's drop it in the middle, one time, let's have it together and then take one off, right? So they'll just come up with any new way. They're not gonna give you the same thing you've seen before. Their goal is not to test how much you can memorize or how you can solve a standard problem. Their goal is to see how clever and creative of a problem solver you can be. Can you take things from all 7 units potentially and integrate them together and solve a brand new unique problem? Because that's what they're testing. How good of a problem solver are you? That's really what the exam is checking. So. All right, any other questions about this FRQ? Okay, let's go ahead and jump into the notes then. We're gonna start a new topic. We're jumping into the last unit of the year. And we've got 3 weeks basically. We're starting it today. Monday's a bit of a wash because it's a short period and the juniors are gone, so we won't be really doing anything new with this unit. But then we'll have basically 2 full long days next week, 3 days the week after, and 2 days the week after that to get us through this final unit of the year, including some review mixed in there and prep for the exam. All right, So, rotational motion, unit 7. This is chapters 10 and 11 in your book. If you're following along in your book, if you're using your book, it's a good resource to read through, good example problems. I still don't think the book's as helpful as the AP Classroom site, but it is helpful. I think the AP Classroom site is your number one go-to for practice and review. And just to be honest, you need to be doing that on your own. Like, I give you some assignments, but some students need a small amount of repetition, they just get it. Other students need much more repetition. And so I'm not gonna require everybody to do everything possible because not everybody needs that, but most of you do. Most of you do need more than I actually assign. And so you should be going through practice problems, you should be doing more on the AP Classroom site than I assign, watching more videos, doing more of the progress checks, if you want to be successful on the exam. I mean, that's just the reality of it. So make sure you're hopefully putting in some extra time whenever you're able, or over upcoming spring break, watching some extra videos, practicing some extra problems. It's really the repetition. We're going to cover everything you need to know content-wise, but the repetition is what's going to move you from a 3 to a 4, or a 4 to a 5, or whatever on the exam. All right, so some of this will be old hat for you because of the math classes you've had. We're going to start with an explanation of what the heck is a radian. And some of you already know and you're really clear with what that means. But for those that haven't really either learned it, or maybe you kind of sort of learned it, but it didn't make sense, we'll give you one pass by at it today. And the whole idea of rotational motion is it's not necessarily moving in a circle. It's just spinning around an axis. Okay, so if I spin a ball on my finger, it's rotating, but it's not traveling in a circle. Okay. Now the Earth is traveling in a circle around the sun and it's rotating, so it's doing both. So some objects do both circular motion and rotational motion, but they are two different things. All right, so for rotational motion, the tricky part is kind of like circular motion, we had to add a new thing, like we had to add centripetal acceleration and centripetal force, we had to add a couple layers. We have to do that again with rotational motion. All right, so we started the year with something that was called translational motion, just objects that went in a straight line. And recently, we talked about the idea of center of mass, that even if you have some weird shaped object, if it's only moving translationally, we can narrow that object down into a dot, and we can just focus on its movement. Did it go on a straight line? Did it curve? Whatever. If it's not rotating, if it's just moving translationally, even if it's going in some weird pattern, doesn't really matter. We can draw it as a dot, we can think about it as a particle, a point, and simplifies a lot. However, now we're talking about not just translational, now we're adding in the final piece of the puzzle, the rotational. Because if you look at this, especially they've intentionally given this weird extended object. It's got a weird shape. And if it wasn't just moving translationally, if it was rotating, that's a whole other kind of motion, right? So translational is just basically moving like it's a single point from one place to another along some path. But if it's rotating, then we've got spinning of that object around some point. So we're going to start initially with this, just objects that are not moving translationally, but they're only moving rotationally. We'll start there, okay? And then we'll get into when it combines both. If it combines both, you're going to have two kinds of kinetic energy. Because if it's moving with both sorts of movement, rotational and translational, now you're going to have it spinning while it's moving through some path, okay? And so that's going to be the final step of this unit when we get to the point where we're combining those two together. It's going to have some kinetic energy along its translational path. It's going to have another kind of kinetic energy as it spins, because that's two types of movement. And so in the last unit, or 2 units ago, I guess, we talked briefly about center of mass. And I mentioned that it would come back in this unit and we would dig into it a little bit more. We'll visit it a couple times. So a couple mentions of it today, that when we talk about something that's moving translationally, we focus on, well, where is the center of mass? That's our dot. We just follow the dot. If it's moving rotationally, we think about the center of mass as the point around which the rest of it rotates. When it's doing both, the center of mass guides us in both things. All right? Any questions about the difference between translational and rotational motion? Is that clear? Okay, so with rotational motion, we've got 3 new variables. So I'll just give you a few seconds without me talking to kind of read this and jot some things down in your notes, and then I'll talk you through it. All right, I want you to just pause for a second and recognize how much you've already learned. So at this point of the year, we've learned every one of these equations. We've learned these bottom 4 here, and we've learned this whole section. Okay. It's just this piece right here. This is what's left. Okay, so you've learned a lot already. Just got this little piece right here that's left. So congratulations, you've come a long way. Now, what do these things mean? You've seen that symbol theta, looks like a 0 with a line through it. And we use that to represent angles. We've used that symbol all year long when we were doing trigonometry and trying to figure out x components and y components. But now we're using it to not just represent an angle that's like a translational movement, but an angle in terms of how far did it rotate? Did it rotate through 30 degrees? Did it rotate through 60 degrees? Did it rotate through 90 degrees? So instead of just saying, oh, it went at 30 degrees relative to the horizontal, now we're talking about how much did it rotate, okay? And so it's a different use of this, and we call that angular displacement. Displacement is the same thing as before. It's how far is it from its initial position to its final position, but not translationally, rotationally, okay? How far did it rotate from its initial position? We use omega, which is the fancy looking W here. Omega represents angular velocity. And so now we're saying, okay, it rotated this many degrees. We're going to call it radians in a minute, but it rotated this many degrees. How fast did it do that? Okay, it rotated 30 degrees in 1 second. It rotated 30 degrees in 2 seconds, right? We're just finding how fast is it rotating. And we use the omega to represent that. How fast is it actually rotating around that center of mass? And then we've got alpha, which is now our 3rd form of acceleration, angular acceleration. And angular acceleration is, okay, well, what if it starts going at this speed, rotating, and then it starts rotating faster, or it starts rotating slower? So I spin a ball on my finger, and then I hit it to make it go faster. I just accelerated it, right? Angularly. All right, so if we change its angular velocity, we're giving it an angular acceleration. But to use these, we have to measure our angles in not degrees. I've talked about it in degrees there because probably that makes most sense in your brain for the majority of you, that degrees just, we can picture that. But to use these mathematically, we actually have to do that in radians, because degrees, that number 360, I don't know where it came from historically, but it's just a random number that's been applied that has no mathematical connection to the actual geometry of a circle, okay? So it gives us a reference point. It's a nice little scale, but it doesn't connect to the fact that it's a circle at all. Radians do, and so that's why we can use radians. So if you've learned radians before, you may have learned it a bunch of different ways, but the basic idea of a radian is it's a way to measure an angle based on the geometry of a circle, instead of just a random scale that goes from 0 to 360, okay? And so it's based on the arc length and the radius. So we're basically taking a certain angle where the radius is fixed because it's a circle, and we measure the arc length, and the ratio of the arc length and radius will tell us the angle, but not in degrees, in radians. So for those of you that have been in math classes where you've been using radians for a while and you have to keep switching back and forth from physics class to math class, now, actually you can leave it in radians for a while because we're going to be focusing on radians. Now, that won't be for good because of physics and because you're going to be tested on everything, you're actually, even within the test, going to have to go back and forth,
Dang.
right? If you're doing something with rotation, you're going to have to use radians. If you're doing something that's translational, you're going to have to use degrees. So, I mean, you could do some conversions to avoid that, but chances are it's going to be easier just to switch that. So keep that in mind that for now, we're going to focus on radians for quite a few lessons. But if it says that it was moving 30 degrees relative to the horizontal for a projectile motion or something, you need to go back to degrees or convert it, but yeah.
How's the calculator like? What does it do differently when you switch it to radians rather than degrees?
It's just switching all the internal calculations to whether they're based on this definition of what an angle is or whether it's based on the 360 total.
Or whether, yeah, I guess whether circles divided into 360. That makes sense.
Yep. All right, so let's look at a few examples here. So an angle measured in radians is the ratio of the arc length to the radius. That's how we define the concept of a radian. So let's start here. We'll go clockwise. In this one, this is, and for those of you that have been through unit circle conversations in your math class, hopefully this looks a little bit familiar. In degrees, this is 90 degrees, right? But when we think about this in terms of unit circle, this is half pi, right? What's pi for a circle? 180. It's halfway around is 180 degrees, that's pi. What's all the way around? 360 degrees is 2 pi, right? Kind of doesn't make sense because a circle should be just 1 pi, but it's actually 2. Let's think of it as a BOGO, 2 for the price of 1. All right, so 2 pi for the whole circle. But here we're only going quarter of a circle, so that's half pi, all right? So the angle would be half pi times the radius, that's how we would find this arc length, divided by the radius. So the radii cancel, that means the angle, while it's 90 in degrees, would be half pi radians. All right? So 90 degrees becomes half pi radians. Now this is 180 degrees, but that's halfway around the circle, which is pi. So if we take pi times the radius to get this arc length, and then divide it by the radius because of this equation, that tells us this angle in radians is pi radians. Now, if you aren't given that kind of information, what if you're actually given the values? What if they just say, oh, the arc length is 3 meters and the radius is 5? Easy enough. 3 meter arc length divided by 5 meter radius is 0.6 radians. Right, so in this class, you're very seldom going to need to convert from degrees to radians. That's in math class, you have to go through that process and do that when you're learning it. This class, they're generally going to tell you enough that you don't have to convert. Okay, not always. There's rare occasions, but usually you can figure out the problem without having to convert. The main thing to remember though is if you're finding angular rotations, angular velocity, angular displacement, angular acceleration, it has to be measured in radians. You can't put it in degrees. All right, so that is the idea behind radians. It's the ratio of this arc length to the radius. Now there's a little shortcut. And it comes in this equation, right? If I multiply the angle in radians times the radius, it'll tell me the arc length. So arc length on this equation is S, but that would also be the displacement along that line, right? So we could call it x if we wanted to think about it as displacement. So if you know the angle in radians and you know the radius that it's traveling along, you could find its linear displacement using this same relationship that defines what a radian is. So I want you to keep that pattern in mind. Angular displacement times the radius gives you the linear displacement. Linear, like it's not really going a straight line, but along the path, okay? Angular displacement times the radius gives us the displacement along the path, okay? So that's a relationship I want you to keep in the back of your mind. And that little relationship, this definition of what radians is, this connection, that's not on College Board. So if you haven't learned that, if that's not something committed to memory, that may be a relationship you want to jot down in your notes. Maybe if you've got that collection of equations that are helpful, but College Board doesn't give you, that one in the blue box right there might be one to jot down. I think probably most of you already put it in your notes, but just a recognition that they don't tell you that relationship anywhere on here, okay? In fact, there's going to be quite a few equations in this section where they don't tell you some of the equations that are going to be super helpful in problem solving. All right, let's move forward. Are there any questions? All right, so angular displacement is the change in position based on the angle, but in radians. So just like any sort of change, we're going to take final minus initial. What was its final, its final position on this circle minus its initial position on this circle. That's our change in angular position. That's our angular displacement, our delta theta. Speaking in Greek here. It has to be in radians though. Okay, it can't be degrees, it has to be in radians. All right, any question about that definition? What we mean when we say angular displacement? What is its change in angular position? Now sometimes they'll ask you to find the angular displacement, and then from that they'll say what was the linear displacement along the arc. Okay, and so that's going to be when you take the radius times that angular displacement to get the linear displacement along the arc. All right. Now how about angular velocity? Well, like I said, if you're talking about an angular displacement, it has to be doing it over a certain amount of time. So if we say, well, it's moving that many radians of change in its position, but it has to happen over a certain amount of time. So if we get the change in position over the change in time, that's our change in angular velocity.
So summary of all physics, change in anything is equal to the final of it minus the initial of it.
Yep. So what was linear velocity? Displacement over time. Angular velocity, angular displacement over time. Right? All right. Okay with that one?
Does that like turn into revolutions or something, or?
You can use it to figure out revolutions, like how many revolutions per second. So, or sometimes they'll say it was this many revolutions per second, and then you know a revolution is 2 pi radians. So then you can plug that in to get your velocity.
Okay.
All right, remember that we're talking about this displacement in radians, so our unit for angular velocity is not meters per second, but radians per second. How many radians is it rotating in a second, instead of how many meters it's moving in a second?
Just from rad seconds.
All right, everybody okay with this one? All right, so notice that if I had a record player or something spinning and I had an object on it, so I've got this object at this radius from the center, like we've got this big disk, but it's this far out. Now, you can see the title hopefully at the top here. Maybe move that down at the bottom so you can, I'll just hide it. The omega, this angular velocity, is the same everywhere, no matter where you're looking at on this disk. If this disk rotates pi radians, then everything on there rotated pi radians, right? But the linear velocity is not the same everywhere. So let's kind of prove that both visually and mathematically. If I rotate it 90 degrees or half pi radians, I can find the angular velocity and I can find the linear velocity. I know that if this arc length is 0.4 meters and it's half pi radians and the radius is 0.255, I know this information, right? So I can plug it in here. My change in angle is 0.5 radians. The time, this is happening in 2 seconds, all right? That's 0.25 radians per second. It went 0.4 meters along this arc in that same 2 seconds. So it's 0.2 meters per second. Now what if we change its position? Right now it's kind of in the middle of this disk. What if I move it out to where it's out on the edge of this disk?
Velocity changes, but angular velocity is the same.
Yeah, if it goes 90 degrees or half pi radians, it's the same, right? It still went half pi radians and it still took 2 seconds. That's not changing. But the arc length is much longer now. And so while the angular velocity is still 0.25 radians per second, it's still, the disk is still spinning at the same rate. If it's sitting out here on the edge instead of sitting in here in the middle, in terms of its speed along the path, it's actually going twice as fast.
Is that only because the radius is half?
Yeah, this they just doubled the radius.
So if you like triple the radius, you go 3 times as fast?
Because if you take the angular velocity, we're going to prove this in a second, times the radius, you get the linear.
Okay, that makes sense.
The way radians are defined.
So if radius increased by 3,
Yeah.
linear should increase.
So that's why we need radians, because if we use radians, it's defined on the geometry of a circle, which means we can use the radius to calculate, go back and forth from linear to angular.
So you just got 0.5 pi from unicircle,
Say that again?
or was that given?
Uh,
How did you know it was 0.5 pi?
Because it's 90 degrees.
So you just use that to unicircle.
All right, so if it's spinning, the angular velocity, doesn't matter where the object is on the disk, the angular velocity is going to be the same as long as it keeps rotating at the same speed. But the actual velocity of the object along the path will increase as it gets further and further from the center. Okay? So if you've been on a merry-go-round, you've felt that. If you're sitting close to the center of the merry-go-round when it's spinning, you don't feel as much, you don't have to hang on as tight, right? You don't feel like you're moving that fast.
Yeah.
If you get out on the edge, you feel like you're moving pretty fast,
I
right?
thought about that.
Playground physics.
We put the Earth really close to the sun.
All right, so angular velocity is the same everywhere, but the actual speed of the object along the path increases as the radius increases. Now, proving that we can just go back and forth here, here's a nice derivation. They would probably not ever ask you to derive this exactly, but I always like to show you as many as possible. So here are the two formulas we have. Angular velocity is change in angle over time. Linear velocity is change in position over time. If I solve them both for time, that should be the same for both objects, right? If you have something rotating on a disk, the time it's rotating angularly should be the same as the time it's rotating along the path, right? The time won't be different. So if we solve them both for time, now we can set them equal to each other because the time for both should be the same. Tracking okay with that logic? Any questions about that? All right, so since the time is the same, let's set those two equal to each other. So the radians divided by the velocity that it's moving angularly will be equal to the distance in meters divided by the velocity that's moving along the path. If we solve it for the linear velocity, just algebra, we're just going to cross multiply the velocity, cross multiply the omega and the theta, and we get angular velocity times the distance divided by theta gives us the linear velocity. But what is a radian after all? Well, a radian is the arc length divided by the radius. And here we're talking about the distance traveled as the arc length. So the angle is the arc length divided by the radius. That's the definition. So let's plug this in for that. We know radius is going to be d over theta. Let's plug that in. D over theta means if we take the radius times the angular velocity, we get the linear velocity. This little equation down here in the bottom, not one that they give you, often very helpful in solving problems.
Mr. Mo, could you go back to the previous slide?
To
I just have a question.
this slide?
For the angular velocity, when you divide on the top 0.5 pi over 2
Mm-hmm.
and it equals 0.25, does that mean you don't like use pi? Because 0.5 over 2 is 0.25.
Oh, it should be, sorry, pi should be there. Yeah,
Oh, okay.
it should be 0.25 pi. I can see if it'll, well, I'll do it later. I'll see if it'll let me edit it. Good catch. Okay, any other questions? All right, last bit here then. If we want to convert, from angular to linear, multiply by the radius. It's the same thing we did for displacement. Same thing we can do for velocity. All right. Now let's talk about acceleration. What if it's not traveling at a constant rotational speed? What if it's speeding up as it rotates? All right, so it'll have some final rotational velocity and some initial rotational velocity. So the change would just be final minus initial, and the time would just be final minus initial. So the angular acceleration would just be the change in omega, the change in angular velocity, divided by time. What is regular acceleration, linear acceleration? Change in velocity over time. This is just change in angular velocity over time. So the definitions still hold. We're just talking about angles instead of linear.
Can you have circular force then?
Rotational force, well, there would be centripetal force. We're going to talk about an element to it called torque, which is coming up next week. And it's not meters per second squared now because we're not measuring how many meters it's moving, we're measuring how many radians it's rotating through. So the acceleration is radians per second squared, not meters per second squared. So similar, but not quite the same. Any questions about angular acceleration? All right, so hopefully you're seeing a lot of similarity. We learned displacement, now angular displacement. We learned velocity, now angular velocity. We learned acceleration, now angular acceleration. There's a really tight correlation. It's just about what's in the numerator. Is it radians or is it meters? All right. You can also convert, so here's another deriving scenario. If we take angular acceleration, change in angular velocity over time, and linear acceleration, change in linear velocity over time, what's going to be the same for both? Time. So if we solve them both for time and set them equal to each other, we've got this relationship. And if we solve for linear acceleration, we're trying to find how could I convert the angular into linear. Well, we've got change in linear velocity over change in angular velocity, but we know that linear velocity, we learned on the previous slide, a couple slides back, we could just take the radius times the angular velocity. And so if we have radius times angular velocity divided by angular velocity, that just simplifies to radius. So this relationship is just radius times angular acceleration. That is another equation College Board doesn't give you, but can be very helpful. Converting from angular acceleration to linear, multiplied by the radius.
Yeah, they don't even have an angular acceleration. Or they do, I think.
They do have angular acceleration on there, but not in this connection, not the way that you can convert it.
Because angular times the radius is equal to the linear.
Which kind of makes sense.
So the angular times radius is equal to linear for all three things: displacement, velocity, and acceleration. So in other words, if we want to get linear acceleration, multiply the angular times radius, just like we did for velocity, just like we did for displacement. The same relationship every time. Angular times radius gives us the linear correlation. All right, questions about that? Those are the three new terms. That's all we're going to cover, new terms today. We're going to look at an example here to finish up, but that's the only new terms. We've covered them all now. All right. So real quick, radians are unitless. It's a ratio. It's a ratio where it's based on the definition of the geometry of the circle. So if we are doing these conversions, like the radius times the angle, the displacement is just meters. So meters times radians just gives you meters. If we're using radius times the omega times the angular velocity, it would look like meters times radians per second, but the radians are unitless, so it just becomes meters per second. Okay. If we're doing radius times angular acceleration to get the linear acceleration, it looks like meters times radians per second squared, but since radians are unitless, it just becomes meters per second squared. Okay. So keep that in mind as you're solving problems. If you do these conversions we just learned, the radians don't carry through. Okay. It's a unitless measure.
Is there any other unitless measures that we know?
We've learned a couple, like coefficient of friction is a unitless ratio. Yeah. So here are the three accelerations we've learned this year. We learned first linear acceleration, change of velocity over time. Now today we've learned rotational acceleration or angular acceleration, which is rotational velocity over time. And we earlier this year in Unit 3 learned centripetal acceleration, which was a v squared over r relationship, a change in direction toward the center. It was being pushed to the center by that acceleration, pushed or pulled. So now we have three kinds of acceleration. So you have to be really careful. If the question asks you to solve for acceleration, you have to be certain which one they're asking about. Are they asking about angular acceleration? Are they asking about centripetal acceleration? Or are they asking about linear, translational? All right, final slide. This one you might want to take a picture of. And we're going to pick up and kind of talk this through on Tuesday. So since we're going to have a lot of people go on Monday, we're going to pick this up on Tuesday. On worksheet 1, you can do as much of it as you can, but what I'd like you to try to finish are the graphing kind of questions. So what is that, the first 7, first 6. So once you get to the word problems, you are going to end up doing all those. So if you want to keep working, you can. But just so the word problems aren't due Tuesday, but the other ones are due Tuesday. Okay. So Monday we're just going to be reviewing test corrections. Tuesday, make sure you got the front of worksheet 1 done, not necessarily the word problems. we'll probably do some of those word problems in class on Tuesday. All right. If I don't see you tomorrow, have a good weekend. Don't forget to get your lab turned in. A few of you made a stack over here to start, but don't forget that lab report's due today.